Geometric sequences are a very common form of sequences where we multiply between each term. The recursive formula we've seen before. We have our common ratio, and we just multiply it times the term before. Explicit we've also seen before, where you take the first term and use that common ratio raised to the power of n minus 1. Then we also have this kth term if we're given something in the middle and we need to find out the first term or some other term. So let's look at an example. Let's say that we're given that A9 is 3 over 256, and our common ratio is 1/2, and we want to list out the first 5 terms. So we use this kth term, so AN equals AK times R to the n minus k power. So A9, we know, is 3 over 256, and then this will mean we've got 3 over 256. Remember, this is -8, and a negative power means we flip it, so we have 2 to the positive 8th power, which happens to be 256. So those numbers will cancel, and our first term is 3. So we have 3, and then we multiply that times 1/2, and multiply times 1/2, and multiply times 1/2, and multiply times 1/2, and then we have the first 5 terms. Now the other thing we can do is if we're given a sequence, like, let's say we have -2, 1, -1/2, 1/4, -1/8, and so on and so forth, and we want to know, is this a geometric sequence? Well, we look at this and we say, what do we multiply to get from the first term to the second? Well, we multiply times -1/2, and from 1 to -1/2 we multiply, and we see that yes, indeed, it is a geometric sequence. We have a common ratio of -1/2, so we can write our general term by putting the first term down and then our common ratio to the n minus 1 power. Now, you cannot multiply these negatives in because we don't know whether this negative is going to be taken away because it's to an even power, or if it's going to have problems with a negative power. Now, you may say to yourself, this is completely irrelevant. You couldn't even think of a word problem to do with this. And I would say, no, that's not true. So we're going to do a word problem, and it's kind of silly, but it'll give you an idea of how you can use these in real life. So I'm going to read this to you because it's kind of long, and then I'll write out what we need to know. So we have 9 cowboys at Chuck Wagon. So imagine, 100 years ago, and they're riding, or I guess probably more than that, 150 years ago. They're taking the cows in, and they're at a Chuck Wagon, and they pass a pot of beans around. Each one takes 1/4 of the contents of the pot as it comes by him. If the last man gets 1 cup of beans, how much was there to start with, and how many cups did each person get? So if you're taking 1/4 of the beans every time, that means that there's 3/4 left of what was in it before. So what you're doing is you're taking how much is in it and multiplying it times 3/4 and getting how much the next person has to choose from, and then multiply times 3/4, and that gives how much the next person has to choose from, and so on and so forth. So if we write this out, now I'm going to do this a little bit differently, and instead of starting with the first term, I'm going to start with a 0 term, because that's how much is in the pot to start with. And then I'm going to have a second term. This is how much is in the pot after the first person took it. And then A2 would be after the second, and A3 after the third, after the fourth, fifth, sixth, seventh, and then after the 8th person took it. So then the 9th person is going to take it all. So this is after the 8th person took it, so we know that how much is there. Right, 1 cup. Because we know that after the 8th person was done, the 9th person got a cup, and they took the whole thing. So we need to figure out how we can start. What did we start with? How did we get here? Well, let's look at this. We know that we're multiplying times 3/4 each time because that's what's left in the pot, because each cowboy is taking 1/4 of whatever's in there. So we take 3/4, so this term is going to be 3/4 of whatever they started with. That's how much is left. And then the second term will be 3/4 of whatever the person before them had, and so on. So this, though, we know would be 3/4 times 3/4 times the original amount, right? And so on and so forth. So what we end up having is, if you look at that, and I want you to go ahead and pause and kind of write this out so you can see what each term would be in terms of A naught. Okay, hopefully you paused it and found that out so that you can see that your general term would be 3/4 to the n power times A naught. So whatever we start with, we multiply that times 3/4 to whatever power, and we'll get what we end up with. Well, we know what we end up with at A8, right? We know what that is. If n is 8, we know that if n is 8, we're ending up with 1 cup. We have 1 cup of beans left. So we can calculate this out. 1 divided by 3/4 to the 8th power. So A naught ends up approximately being 10 cups. So originally we started out with 10 cups of beans. So if we look at our sequence as it is, since we're looking at this as how much is left, then this person, we started out with 10 cups of beans, and then after the first person took it, we have 7.5 cups left, because we multiply times 3/4, and then multiply times 3/4 again, and multiply times 3/4 again. I'm running out of room here in front of these. So then the A4 person is going to have 3.164, and then the 5th person 2.373, and then this is how much is left each time. So that gives us how much was left, but that doesn't answer the question. What we wanted to know is how much each person got. So each person took whatever, if you take what's left in the pot and subtract what was left after they took it, then you'll get what was left, what they actually ate. So this person, we take 10 minus 7.5, and that gives us that the first person got 2.5 cups of beans. And then we take the 7.5 minus the 5.625, and we have 1.875, and so on and so forth. You just keep subtracting. And then I'm going to skip down to the next line here. And you see that it is not always the worst thing in the world to be the last one getting the food. So if they're actually taking the beans this way, the first few people, 1, 2, 3, the first 4 people got a little bit more than the last one did, but these 4 people after that, they got a lot less. Now, it's kind of a silly problem, but those kind of things that is kind of a example of how you would use geometric sequences in a real world example. So hopefully that helps a little bit, and we can make sure that we're paying attention to being careful to dish out the beans more evenly. So geometric sequences, make sure you understand recursive formula and explicit formula, and how to find whether it is a geometric sequence or not, and how to find that general formula even if it's in a word problem.